In this video, we'll be going over how to simulate and optimize Chevron's TAME plant. So it consists of a primary reactor followed by a TAME distillation column, the methanol extraction column, and the methanol recovery column. The first thing we need to do is to select our components. To do so, go to component selection and choose the 5 components that we're going to be working with. Pentane, water, methanol, isoamylene, but otherwise it's known as 3-methyl-1-butene, and TAME. Click OK when you're done. Then we need to select our thermodynamic system. You can choose Pang-Robinson. And then for distillation columns, we'll use NRTL. And we can leave it as single liquid phase only. For an extraction column, however, we want to select Unifact. And we want to make sure to enable 2 liquid phase calculation. Click OK when finished. Reaction data is also provided for our primary reactor. Go to Input, Reaction Data. I'll say a reaction name is TAME. Name is TAME. And the reaction is defined as methanol and isoamylene as our reactants and TAME as our products, the 1-to-1 stoichiometry. So methanol, isoamylene is 1, TAME is 1. Click OK, OK, OK. And now we are ready to start simulating. To start off, 3 streams will enter a mixer, which is fed to the primary reactor. We have a mixer. We'll connect 3 streams. Stream 4 leaves the mixer. Stream 4 leaves the mixer to our primary reactor, and we'll use a conversion reactor to simulate. Stream 5 leaves the conversion reactor. Stream 1 is our recycled methanol, and it's at a flow rate of 250 pound-moles per hour. It's at a temperature of 80 degrees Fahrenheit and a pressure of 100 psi. Stream 2 is your tankage methanol at a flow rate of 276 pound-moles per hour, and it's at a temperature of 135 degrees Fahrenheit and a pressure of 100 psi. Stream 3 is the product from your selective hydrogenation reactor. Reactor product. And it has isoamylene at 345 pound-moles per hour and pentane at 605 pound-moles per hour. And it's at a temperature of 135 degrees Fahrenheit and a pressure of 100 psi. The conversion reactor is adiabatic, so we have a fixed duty of 0. The reaction set name will be whatever we called earlier, so I called it TAME. And there's an 80% conversion of isoamylene. So for the extent of reaction, change the stoichiometry to isoamylene and specify 80% conversion. Okay. Now run your simulation. Simulation, and it should converge. If it shows something other than blue, then double check your inputs. We also want to generate a stream property table. So you go to Output, Stream Property Table, and then we want to add stream 5. Material balance list. Click OK. This. Now we're ready to start with the TAME distillation column. For the TAME distillation column, we want to initially assume 30 theoretical trays. So add a distillation column, assume 30 theoretical trays, and connect stream 5 to your column. We also want to add streams that are leaving the condenser and reboiler. So stream 6 will leave the reboiler, and stream 7 will leave the condenser. But it should leave the condenser as a liquid and not a vapor. So on the bottom here is a liquid. The top is the vapor. So we want to connect to the bottom. In the distillation column, we want to change our thermodynamic system to NRTL, and the top tray pressure is maintained at 64 psi. And pressure profile, say the top tray pressure is 64. We also want to have the top product, which is stream 7, to contain 0.008 mole fraction of TAME, and the bottom product, stream 6, to contain 0.04 mole fraction of pentane. So in performance specifications, I'll say no to this. Those would be your two parameters. So parameter 1 is stream 7, which is your top product. Should have a composition of TAME to be 0.008. And stream 6, which is your bottom product, composition of pentane to be 0.04. Click OK. In feeds and products, we'll assume that the feed stream, or stream 5, enters tray 5. And performing a material balance with TAME and pentane on the column should yield a bottom flow rate for stream 6 of 273.235 pound moles per hour. Click OK. Okay. Now run your simulation. So initially it does not converge. When we check the error, it says that the number of iterations was reached, so we'll increase the number of iterations. We'll increase it to 200. Running your simulation again, it should now converge. The top product of the TAME column, so stream 7, is fed to the methanol extraction column that operates at 85 psi. So that means a pump is required between these two columns. So we'll add a pump. We'll connect stream 7 to the pump inlet. And stream 8 as the pump out to the pump outlet. And we'll specify the outlet pressure to be 85 psi, and we'll change the thermodynamic system to NRTL. Should now converge. Now notice that stream 5 is yellow. This is nothing to be worried about. It's just a difference in thermodynamic system that we're using, because the distillation column we're using NRTL, but for the reactor we're using Peng-Robinson. Now we're ready to start our methanol extraction column. To simulate an extraction column, we can use a distillation column, but deselect the condenser and reboiler. We'll assume 20 theoretical trays. We connect stream 8 to your extraction column. And the water that's used to extract the methanol is recycled from the methanol recovery column. But we can initially specify this as an input stream. So this will be stream 9. The water flow rate is 1,550 pound moles per hour. And it's at a temperature of 90 degrees Fahrenheit and a pressure of 85 psi. Stream 10 will be your overhead, and stream 11 will be your bottom product. The water enters from the top of the extraction column, and the top product from the TAME column, which is stream 8, enters the bottom. So we'll adjust the feed trays accordingly. Pressure profile first, 85 psi. In feeds and products, stream 8 enters tray 20, stream 9 enters tray 1. The overhead product, which was stream 10, leaves at 920.168 pound moles per hour. Click OK. Lastly, we need to change the thermodynamic system to unifact. So we'll change the algorithm to liquid-liquid, and calculated phases should also be liquid-liquid, and your thermodynamic system to unifact. Click OK. And now run your simulation. Once it converges, now we're ready to move on to the methanol recovery column. One thing to note about our methanol recovery column is that the bottom product is used to preheat the feed to the column before being further cooled and then sent to the extraction column. But we first want to make sure that the column converges before adding the preheater. So we'll add a distillation column, And we'll assume 30 theoretical traits. And we'll connect stream 11 to your column. Stream 12 will leave the bottom reboiler, and stream 13 will leave the condenser, but it should leave as a liquid. In your distillation column, you want to change the thermodynamic system to NRTL, and the top tray pressure is maintained at 85 psi. We also want the top product, which is stream 13, to contain 0.0002 mole fraction of water, and the bottom product, stream 12, to contain 0.002 mole fraction of methanol. So we'll specify that under performance specifications. So stream 13 has a composition of water, 0.0002. Stream 12 composition of methanol to be 0.00. In feeds and products, we'll assume that the feed stream, or stream 11, enters trait 5, and the overhead product, which is stream 13, is eventually the recycled methanol that re-enters your primary reactor, and that is 250 pound moles per hour. After running our simulation, it converges. We want to add stream 11, 12, and 13 to your stream property table. Notice that stream 12 will be the stream that is preheating stream 11 before being sent back to the methanol extraction column. So we need to look at the temperatures for stream 11 and stream 12. Stream 11 has a temperature of 163.872 degrees Fahrenheit, while stream 12 is 315.599. So that means in our heat exchanger specification, we'll have to specify a temperature that is between these two values. Because the top product of the methanol recovery column, which is stream 13, is the recycled methanol, and it's currently at 85 psi and 232.896 degrees Fahrenheit, which is shown in the stream property table, we need to add a pump and a heat exchanger to reach our target pressure and temperature of 100 psi and 80 degrees Fahrenheit. So we'll first add a pump. We'll connect stream 13 to pump inlet and stream 14 to pump outlet. We'll specify the pump outlet pressure to be 100 psi, and we'll change the thermodynamic system to NRTL. Stream 14 enters your heat exchanger. And stream 15 will leave your heat exchanger. Now the heat exchanger should be specified as the hot side and not the cold side, because you're cooling it from 232.89 degrees Fahrenheit to its eventual target temperature of 80 degrees Fahrenheit. So under specifications, we want to change the hot product temperature to 80 degrees Fahrenheit. And lastly, we'll change the thermodynamic system to NRTL. And then we'll run our simulation. For the preheater, we want to add 2 heat exchangers. And we'll connect stream 11, which is the bottom product of your extraction column, to the preheater. Stream 16 will lead to the column. So stream 11 and stream 16 are the cold streams, while stream 12 and stream 17 are the hot streams. So remember, in stream 11 and 12, the temperatures were 163.872 degrees Fahrenheit and 315.599 degrees Fahrenheit. So we want to choose the hot product temperature to be somewhere between those two values. So we'll choose 300 for our case. So 11 and 16 are the cold, 12 and 17 are your hot. We'll specify the hot product temperature to be 300. So we want the cold side thermodynamic system to be UNIFAC and the hot side to be NRTL. This heat exchanger is good. The second heat exchanger is the hot product that's being further cooled to 90 degrees Fahrenheit. So change this to hot thermodynamic system to NRTL, and the specification of our hot product temperature to be 90 degrees Fahrenheit. And then in your distillation column, we'll assume the new feed stream, which is stream 16, to enter tray 5. Running our simulation, and it should now converge. Once everything converges and looks good, we can work on optimizing all of the columns. So we'll first start with optimizing the methanol extraction column, the one in the middle. We want to determine the number of trays so that the bottom product of your extraction column, so stream 11, does not exceed 0.003 mole fraction of pentane. So at 20 trays, the mole fraction is already below that threshold. So it's at 0.001 as indicated in the stream property table. Therefore, adding additional trays does not do anything, so we can reduce the extraction column to the minimum number of trays, which is 2. So we'll change the number of stages to 2. And stream 8, which is the top product of your TAME column, enters tray 2. We'll rerun the simulation to make sure it converges. It does, so we're good. Now we can move on to optimizing the TAME distillation column. To optimize our TAME distillation column, we need to set up a case study. But before setting up a case study, we need to determine the minimum number of stages that our column can have while also being able to converge. So we'll first try 10 stages. Running our simulation again. It converges at 10 stages, so we're good. To set up a case study, you go to Input, Case Study, and we want to define our case study. So the parameter that we're changing is the number of trays. And we're changing it from cycle 1 to cycle 21 because you know the solution converged at 30 trays. So cycle 1 is cycle 21, and a step size of 1. For results, you can plot either reflux ratio or the condenser and reboiler duties. We'll plot both. So column 1, reflux ratio. And in execution options, we want to execute the base case and the specified cycles. So start cycle 1 and cycle 21. And then we want to reset the base case results before each cycle. Click OK. We'll run our simulation. Once post-run calculations are completed, then we can go to output and plot our results. So in reflux, our x-axis is our number of trays, y-axis is the reflux ratio. UL plots should look something like this. Click OK. You can also export this data to Excel. We can also plot the condenser and reboiler duties. So column, heat duties, condenser. Reboiler. Click OK. And then we'll run. Then in output, we'll plot our duties. X-axis is your parameter, y-axis 1 is your condenser duty, Y-axis 2 is your reboiler duty. And then you should get plots for your condenser and reboiler duty. Again, you can also export this to Excel, or you can read off from this graph to choose the optimal number of stages. Once you decided on an optimal number of stages, you want to change your column to that number. I'll choose 16. And then make sure to deselect your case study before rerunning it again. Okay, it converges at 16 stages. Now we want to optimize the feed stream tray. So the feed stream is currently at tray 5. So we'll set up another case study. Our parameter we're changing this time is the tray location and the feed stream, which is stream 5. And we'll run the case 11 times. So from cycle 1 to cycle 11 with a step size of 1. The results, again, we can plot reflux ratio and the duties, plot both. And we want to select base case and specified cycles and reset the base case results before each cycle. Run your simulation and wait for post-run calculations to be completed. Now we can plot our reflux. You can view your plot. And we can do the same thing with your duties. Duty boiler. Base case specified cycles, reset the base case. So we're good. Oops. Run again. And then we'll plot. And this should be your condenser and reboiler duty. Once you determine your optimal feed tray location, you want to input that in your distillation column. We'll say optimal for us is 9. And then we'll deselect the case study and run it again. The steps to optimize the methanol recovery column is the same as the TAME distillation column. However, we have to make sure to exclude the preheater when running the case study, otherwise Pro2 will crash. To exclude the preheater, we'll right-click the heat exchanger and select Exclude Unit. Additionally, the feed stream, which enters tray 5, results in an absurdly high condenser and reboiler duty value. You can see this by pulling up a unit operation property table, select column, and add all units. So it currently has a duty in somewhat billions BTU per hour, which is not ideal. So we have to first adjust the feed stream tray to a value that will lower the duties by placing the feed stream lower in the column. So we'll try 15. Running it again gives you somewhat better duty, but not ideal. But it's enough so that we can start varying the number of trays to find our base case. So we'll go with 20 stages. Now we can set up our case study. We'll go to Input, Case Study, define it. The first thing we're changing is the number of trays. And it converged at 20 stages, and we initially assumed 30 stages. So we're going to have 11 cycles with step sizes of 1. For results, you can choose reflux ratio or duties. I'll show both, but we're going to do reflux ratio first. Select base case and specified cycles, and reset the base case results before each cycle. Run your simulation. And then now we can output our plot. X-axis is your number of trays, y-axis is your reflux ratio. So this is what your reflux ratio versus number of trays should look like. We'll show it with the duties as well. Condenser duty. And reboiler duty. We'll run it. And then we'll plot. X-axis is your number of trays, y-axis 1 is your condenser duty, y-axis 2 is your reboiler duty. So this should be what your graph looks like. Once the number of optimal trays has been decided, we can optimize which tray the feed stream should go. So we'll first get rid of this. And we'll change your number of stages to your optimal. So here's 22. We have to deselect the case study. We're running it. And then now we can run our simulation. Okay. It converges. So now we can optimize which tray the feed stream should go to. We'll set up another case study. We're changing the tray location, feed stream, which is stream 16. We're going to run it 6 times, the step size of 1. For results, you can choose both. So reflux ratio or duties, select base case and specified cycles, and reset the base case results. Run your simulation, wait for post-run calculations, and then plot your data. So this should be what your reflux ratio against your feed tray location should look like. For duties, we'll change reflux ratio to condenser duty. We'll add another. Reboiler duty. Click OK. We'll run our simulation again. And this should be what our condenser and reboiler duty should look like against our feed tray location. Once the optimal feed tray has been determined, you can deselect the case study. So we'll deselect it. And then we'll change the feed tray location. So we'll go with 19. And we can run it again. And once your case study is done, so this is your optimized methanol recovery column with 19, with the feed tray at tray 19, or the feed stream at tray 19, and the total number of stages being 22. Now you can include your heat exchanger and run it again. So with the optimized TAME process, you can find the required dimensions of each column and reactor, as well as the capital cost. And this is it. Thank you for watching.